Eric Burgess here. The possible average number of friends a person has on Facebook is 240. The population standard deviation is 39. A random sample of 60 high schools in a study showed the average was 280. At an alpha of 0.05 or a level of significance of 0.05, is there sufficient evidence to conclude that the mean number of friends is greater than 240? So our first order of business here is we should identify the null hypothesis. Let's just move this out of the way. And we should identify the alternative hypothesis. So first we'll write this in purple. Hypothesis. And I'm sorry if I misspell this. I think that's how you spell it. So our null hypothesis is going to be H naught, and it always gets that the mean is equal to, right? Because we're going to be talking about the average, and then the alternative, sometimes called H1 or HA for alternative, is that the mean is something else. So looking at this, we see that the possible average number of friends for a person has on Facebook is 240. So we think that the case is that it's 240. So the mean is 240. That's what we think the mean is. But then coming down here, we say we want to conclude that the mean number of friends is greater than 240. So since we want to conclude that it's greater than 240, we think no, the mean's actually bigger than 240. So these are our hypothesis. And we think that it's greater than because we want to use this word here, is greater than. So that's how you know to use is greater than. Up next, looking at this, we need to identify the claim. So which one of these is the claim? Well, we're going to look for what we're trying to conclude. So we're trying to conclude that the mean number of friends is greater than. That means that the claim is going to be the alternative hypothesis. So I'll write that here in blue. This one is the claim. Now that we have the claim and we kind of know what we're working with here, we should get a test statistic. You could also draw a picture as well. In fact, I think probably a wise thing to do before you do any of that is to pull all the information out of the problem. So right now, we've got a mu that's 240, and that's just from the first sentence. The population standard deviation is 39. So population standard deviation is sigma, that's 39. And the fact that this is sigma and not an S, this is a population standard deviation, this also informs us that we are working with a z-score. So that's what we're given with this sentence. The next sentence, we have a random sample of 60 high school students. So a random sample, this is the number, right? So we know that that is given to us by n. So n is 60. And we're shown that in a study, the average was 280. This 280 is connected to the 60. So this was from a sample of 60. So that means that this is a sample mean, an X bar. And this is 280. And then we are given alpha just directly. So isn't that nice? So alpha is equal to 0.05. We're going to need this to get a critical value, right? To decide if something should be rejected, if the claim should be rejected or not. So, okay. Having all this information, let's do a test statistic. So we're going to get a test stat. And we're using a z-test. Specifically, z-test. And this is because of sigma. In fact, I should write this the other way around. The sigma implies a z-test. So now we need the z-test formula. If you don't remember, you could just look in your notes. You should have it. Most professors are fine with you having a collection of formulas to bring into the exam. It's kind of worth memorizing if you're going to be doing this a lot. So z, right, it's the same thing as the previous z-score formula. It's the mean minus, or my bad, it's the x bar first. X bar minus the mean. Because if we're above the mean, we expect it to be positive. If we're below, we expect it to be negative. So it's got to be x bar first. Over, and it's going to be sigma, but since we're dealing with averages, there's also going to be a radical n on the bottom. And this is the formula for testing and finding a z-score. So using this formula, we have already found a bunch of this stuff from up there. So this is the same thing as x bar is 280. The mean is 240. And sigma is going to be 39. And radical n, oops, let's see if I can write that a bit better, is going to be 60. So plugging this into our calculator, we will get our test statistics. So let's pull our calculator out. And I'm going to go ahead and just pop this in. I'm going to assume you're a little more comfortable with using your calculator at this point, whatever calculator you're using. So I'm not going to explain how I get to certain menus. And so we've got 280 minus 240. I do see a lot of students, though, do this in multiple steps and mess it up. Order of operations, right? Do the top separate from the bottom. And remember to type it in with the square root. Square root needs to happen, then the division needs to happen. If you do what I do, you can just type it all in using fractions. So we need another fraction. So I'm going to hit the green key. And then this y equals brings up a fraction button. So you can just hit enter. It'll let you type a fraction. 39 over and then square root of 60. And we hit enter. We get out a decimal of 7.94. Okay. So this is the number of standard deviations away from the mean if the mean were 0 and the standard deviation were 1. So we can now graph this on a standard normal distribution. So if we go ahead and just sort of draw one here, and right, they just go off to plus or minus infinity. So our middle is 0 because we're dealing with a z distribution, right? And z distributions always have a mean of 0 and a standard deviation of 1. You could also get these numbers, by the way, using a calculator. If you go into stat, go over to calculate and then tests at the very top. And then you want to do a z-test. So you can go ahead, you can do a z-test. And we have statistics, right? These numbers up here are statistics. So we're going to use the stats. If you had been given numbers and you had to like compute the standard deviation, you could actually tell it to use data instead. So our mu naught, well, that's the same thing as what we have here, mu, because this is like the null hypothesis. So this is going to be 240. We enter, and then for this, sigma is 39, x bar is 280, n is 60, and our alternative hypothesis is what's given right here. So we say that the mean is greater than 240, so we're going to copy this symbol as greater than, meaning that this mean, look at this. So they're comparing it to the mu naught, and mu naught over here is 240. We're saying this is bigger. So this mean is bigger than this mean. You notice how this is mu naught and this is regular mu. So we're saying that this mean is greater than, so we want that one. And there's actually, you can actually have it draw it for you, which is kind of cool. And this also gives you the p-value really conveniently. So you could go ahead, hit draw. It'll graph it. It gives us a p-value of 0, an extremely small p-value, and z. Now you notice there's like, you can't even see shading. There's no shading because 7 is ridiculous. 4 is considered enormous. 7 is like astronomical. So we should draw in our alpha. So our alpha is 0.05. And we are doing a greater than test. So that means it's going to be a right-tailed test. So that means that we've got an alpha area here, this shaded region, and it is 5%. We need to find the z-score, because we're doing a z-distribution, that goes with 5% of the curve. Now, remember, this distribution is symmetric. So if we find the value that goes with this 5%, because this is also 5%, this is going to be the negative z value. So if we just find this one in the chart, we can just flip it and get the positive version. So we're going to look up 5% in the chart. Now 5% is 0.05, right? Same thing as 5%. So we're going to go to the standard normal chart, and we're going to look on the negative side just because it's easier. We could also look up 95%. And the reason we can do that is because if we come back to this, well, if this is 5% and the chart gives area to the left, all this area must be 95% because, right, the entire chart is 100%. So you can look up 95% as well. But using symmetry, we could just look up 5% and make it positive, which is what we're going to do. So we're looking for 0.05. So here's 0.02, 0.05. It might not be exactly on here, but we can get close. Okay, so it seems that we're between these two. So we've got 0.0505 and 0.0494. So this one would need 0.006 to get up. This one we need to go down 0.005. So you honestly, you could pick either one of these. I'm going to go with this one. So looking at this, if we draw lines out and up, like so, we can find the z-score. So it's negative. Well, let me do this here in a different, let's just circle in black. This would be negative 1.6. And then we'd add on a little 4 at the end. So negative 1.64 would be the z-score that goes with 5%. And that's for the negative 5%, negative 1.64. So this means that the z-score we're interested in is positive 1.64. And then I'm going to erase this because it is a one-tailed test. I don't want to confuse you. It's a one-tailed test. I only showed that to demonstrate symmetry. So this is our critical value. If the z-score goes past this value, then we say that there is evidence to reject the null hypothesis. We don't think the null hypothesis is right. Well, we got 7.94 for our test stat, right? That's like, if this is 1.64, that's like way out here. So if this chart were to keep going and going, it'd be way, way, way out here. 7.94, definitely in the shaded area. This is crazily in the shaded area. So since it's in the shaded area, we say that we reject the null hypothesis, reject HO. And the reason we reject HO is because we're in the shaded area. We're so far away from this being true that it's very unlikely by chance that it's actually true. And so that's why we say, okay, we reject HO. If we reject HO, then that means that we don't think HO is correct. We think it's wrong. And if we think HO is wrong, that means the alternative we do think is right. We have evidence to support this. So we say, well, this is our claim. And so the next statement always has to do with the claim. And so we say, so the claim we think is true because we have evidence to support it since we don't think HO is correct. The null hypothesis doesn't seem right. So we're going to say there is evidence to support the claim. Now, evidence to support the claim, and some professors will want you to be more specific. So you might say there is evidence to support the claim that, and then you could add on the number of friends, the average number of friends is greater than 240. Basically just the end of it, whatever you're trying to claim. So some professors are not happy with you just saying this much. You might have to include a little more to show that you've now proven something about the study, right? You've now got a hypothesis, or not a hypothesis per se, but a result, evidence that is pretty convincing statistically. So that's what you're going to do. Now, there's another way to get some of these values using the calculator. So for example, if you want to find the critical value using the calculator, well, we can do that because the calculator has an option for putting an area and getting a z-score. So to find this critical value using the calculator, you can go to the distribution menu because we're doing a standard normal distribution. So we're going to hit second and then distribution. And then we're going to go down to inverse normal because that's going to invert this and tell us, we'll give it an area and it'll tell us a z-score. So we're going to do that. And, well, let's clear everything. I don't know why it brought up that option. Normally, there we go. Yeah. So you could enter things in via parameters with semicolons, but it should bring you to this. If it doesn't, just clear everything out. So the area we're looking at is 0.05, and so that's going to be that. And since we're working on a standard normal curve, because we're doing z-scores, remember, we're going to give it a mean of 0, a standard deviation of 1, and we're going to paste, and we get out negative 1.64. And remember, that's the negative side for this 5%. So we're going to flip it, make it positive 1.64. In fact, if we come in, and wrong menu here. If we come in and put in an area of 0.05, well, if we put in 0.95, we'll actually just get the same thing but positive, as you can see. So there you go. There's a little bit of evidence for that. And you would compute this using the calculator, or you could do what we did before, which was to go to tests, a z-test, and then you could put it all in. Now you could hit calculate or you could hit draw. If we hit calculate, it'll give you the z-score and it will give you a p-value. So that other one was rounded. This one is not. And remember that if the p-value is less than alpha, that means, so here's alpha is 0.05. This p-value is absurdly small. Negative 16. That's 15 zeros before you even get to the first 9, the first number. It'd be 0.0000000, 15 zeros, and then a 9. Insanely small, basically 0. And so this is definitely smaller than alpha. So if you were going to use the p-value method, you could say p is less than alpha, therefore reject the null hypothesis, right? Because if p is less than alpha, that means the area covered by p is less than this shaded area, which means that your test stat would be in this black area. So you would get the exact same conclusion. But there's a couple ways to compute everything. You could do this with Excel too, as far as finding these values. It's really a lot of chapter 6 kind of stuff using the standard normal distribution and figuring out what z-scores go with what. But that is how you would do this. If you have any questions, feel free to let me know down in the comments. Subscribe, and we'll catch you in the next problem.